Hello and welcome to our today's webinar about the application of CFD for the design and analysis of duct systems. Today we want to learn and understand how fluid flow simulation can contribute to both design and optimization of HVAC equipment and systems. Therefore, we will talk a little bit about fundamentals of CFD as well about hands-on aspects. And I will show you an example about the application of CFD for optimizing the HVAC ducting part. First of all, I would like to introduce myself. My name is Milad, and I've studied mechanical engineering with a focus in biomedical engineering and process engineering. And in the last 10 years, I was working on and with different simulation tools in different industries, including automotive, motorsports, and aerospace. And as a part of my role as a product marketing manager here at SimScale, I regularly organize and conduct workshops and webinars which introduce interested engineers into the world of CFD and FEA. In the case you have a question regarding that webinar or CFD in general, please don't hesitate to contact me, and therefore I suggest just to drop an email on mmurphy@simscale.com. Alright, now let's take a look at our today's agenda. As I mentioned at the beginning, we will talk about the benefits of using simulation, and we will take a look on this from both perspectives, a general one as well a perspective which is related to people working in the HVAC industry. Followed by that, I will introduce you to SimScale, the world's first web and cloud-based simulation platform which gives access to all engineers to simulation for free through the web browser. And then we will have some time to discuss the knowledge gained before in the context of HVAC duct system design. We will talk about how different type of engineers, or let's say in different roles, can use simulation for the projects. And as I mentioned, we have prepared a short live demo project where I will show you how such a simulation can be leveraged in order to reduce the pressure drop inside the ducting system. Yes, and finally, we will have time for a Q&A where I will try to answer all your questions related to CFD and how it can be used for ducting system design. So therefore don't be shy, and you can write all your questions inside the question toolbox, which is a part of the software GoToWebinar we are using to stream this live webcast to you. And I will try to answer the questions directly on the fly or latest during the Q&A. And just because the question, I got asked this question several times, yes, we are going to record this webinar and all registrants will be provided with a link to that recording. Well, let's start to talk about the benefits of simulation. And yeah, first of all, fluid flow simulation, also called CFD, which stands for computational fluid dynamics. It's a quite new technology which has its roots in aerospace and automotive engineering. And the great thing about CFD is that it provides you with a detailed picture about the flow field. And in contrast to other methods and tools used like the Bernoulli equation or loss factors, it will really give us detailed information about the pressure, velocity and temperature of our fluid at every point at any time step. And in contrast to physical testing, you don't need to manufacture a physical prototype, and therefore CFD allows you to perform such analysis just based on a CAD model. Yes, and now let's take a deeper look at the benefits and advantages of using simulation. As I mentioned, first of all, CFD is a kind of virtual experiment, so it allows us to predict the performance of objects which are related with airflow, just based on a CAD model. And this allows us, in the end of the day, to test different designs and to judge about the performance and efficiency at a very early design stage. And since we don't need to build any physical prototype for that, it saves a lot of time and money. Just imagine if you, let's say, want to design a very simple ducting segment. And usually when you follow this old way of designing products, first of all, you will start with making a rough sketch. Then, because you need to manufacture a prototype, you need to really design all the details. It will take you a lot of time, weeks to months. You need to order the materials, build the single part, assemble everything together. So you will lose 6, 8, or 12 weeks of design time just because you're waiting for your model to verify your assumptions. And that's the very first and big, let's say, benefit of simulations. It's really quick, and usually just in a fraction of the time you would need to prepare a physical test, CFD will provide you with a lot of detailed information about your product and the flow field. And this necessarily minimizes the risk of failures, because CFD allows you to start to, let's say, consider different what-if scenarios and to test different approaches at the very early design stage. And usually optimization is done at the end of the product development process. And this is not very smart, since, let's say, most of the performance and the other characteristics related, for example, with the cost of the product are defined at the very early beginning of your product design process. What also is a very big advantage of CFD in general is that it provides us with a different kind of results. When we do physical testing, the amount of information we will acquire through this is limited to the, let's say, number of physical quantities we are able to measure. So let's say if we want to measure the flow field of the HVAC duct, we will only get as many informations as pressure probes, for example, we have. CFD, in contrast to that, actually gives us for every point of our domain detailed information about the physics. So CFD is not only quicker when it comes to test something, but it's also better in explaining not only what is happening, but why it is happening. For example, if we have a, let's say, a increasing pressure drop for certain velocities or certain mass flow through our system, simulation can tell us exactly why this is happening, example given the flow separation induced. And in the end of the day, CFD in general, and independent in which application we use it, helps us to design better products in a shorter time frame with a smaller budget. Let's see, it seems like some people are raising their hand. So you all can hear me properly, right? So everything is working. Can you please raise your hand because someone was writing he can't hear me. Can you please raise your hand in the case you hear me? Perfect. Great. I see some hands. Sorry for that, guys. I just wanted to make sure that everything is working from a technical point of view. All right. And now let's try to adapt these benefits to the AEC industry and to understand how in particular CFD can help when it comes to design systems or even whole buildings. So AEC stands for Architecture, Engineering and Construction, and then include basically everything related to the design and construction of buildings. And CFD, or especially SimScale, is actually used by a lot of very big and also smaller companies in the field of AEC. And first of all, CFD is for sure used for optimizing and validating HVAC system and parts. So let's imagine you designing a big residential building or a big office building where you have a HVAC system for ventilation. And CFD can be used on the one hand to optimize, let's say, single components of this HVAC system, including fans or ducting segments, but it can also be used for investigating and optimizing the full system and to understand the interaction between different parts and segments. And this is mainly used to improve the energy efficiency of such systems. For example, when it comes to HVAC ventilation systems, we are talking about the pressure drop, which we want to minimize, since this is directly contributing into the energy amount which is needed to run the fans. But CFD is not only limited to improving the energy efficiency of HVAC systems, but it can also be used, for example, to understand and improve the air quality control and contamination. That's, for example, when you're going to design a factory line where you have some, let's say, toxic fumes, or also for residential or office buildings. It can be used, for example, to improve the smoke removal in the case of fire, or to optimize the thermal comfort, which is not necessarily the same, or let's say, which isn't necessarily associated with the same design changes like improving the energy efficiency. However, it can be very important. As you know, it's not only about providing the right amount of air, but also provide it to the right place inside the building. But beside everything which is related to what is happening inside the building, CFD can also be used to understand or investigate the interaction between the building and the surrounding air. For example, we have a lot of customers using CFD and the SimScale platform for predicting wind loads on facades and large buildings. Alright guys, now I would like to quickly introduce you to the SimScale platform. Just remember, in the case you have questions, you can directly drop them into our question toolbox. Well, so let's talk a little bit about SimScale. And from what I've told you about the benefits of simulation, you must think that it's a super important tool which is used by a majority of engineers. Unfortunately, it's exactly the other way around. Also, there is this big advantage. Simulation is still only used by a minority of 5% of engineers. And there are a lot of reasons why only a fraction of engineers can use this, let's say, traditional on-premise simulation tools. And 5 years ago, when SimScale was founded, we all shared the vision of democratizing simulation and making it available to every engineer in the world. And back then, we found out there are actually 3 main barriers which are stopping a lot of engineers from adapting these tools. And to put it in a nutshell, in the end of the day, on-premise software comes with a lot of high upfront costs for software licenses, and here we are talking, let's say about the price of a mid-class car every year, which you need to pay to the software vendor. You need to buy dedicated hardware, which is super powerful and also super expensive at the same time. And in the past, with traditional tools, you also needed to have a very trained staff, and at the end of the day, you needed to have a simulation expert in your team which is able to use that software. And the vision of SimScale, as I mentioned, is to make simulation accessible to everyone, and therefore we invented the first web and cloud-based simulation platform, which means SimScale is the fully advanced 3D simulation platform which you can use with every computer. And the only thing you need is a web browser, a standard web browser, and a working internet connection. Everything else, the software, the storage, and the computing capacity comes from the cloud. And therefore, SimScale allows you to use simulation independent from your local hardware software, and in a very flexible way, since you don't need to buy anything, and you will just, in the end, pay that simulations that you use yourself. And as I mentioned, SimScale is the first web and cloud-based simulation tool. But what does that mean? First of all, SimScale is what we call an all-in-one tool. So in our today's webinar, we will talk only about SimScale CFD capabilities. But in the end of the day, SimScale can be used for computational fluid dynamics, so for fluid flow simulation, as well for structural mechanics, and for thermodynamic simulation. And all the simulation can be set up from the same UI. And at the same time, SimScale comes with real-time support. Since SimScale is cloud-based, you are not buying a software or access to a software, but you actually get a full package, including of the computational power, the software you need, as well as real-time support. And there you can choose between chat, phone, and email. So you can contact our support team through different channels. And besides standard support, we also offer consultancy as well as free webinars and training. SimScale is fast and easy. Since it's cloud-based, you never need to wait for a long time for your results. A big problem with on-premise software is that you are limited by your computational resources. Let's say you want to perform a simulation of the HVAC system. You need to wait for until one simulation is finished until you can start the next one. And through the cloud-based approach of SimScale, you can basically access as many computational, let's say, use as many computational resources as you want and scale your project with your needs. And at the same time, SimScale is very cost efficient. So actually, you can use SimScale completely for free with our community plan. And depending on your needs, we also offer different professional plans which come with additional support, consulting, and the ability of create private projects. But it's not only about the costs and the speed where the cloud-based approach of SimScale paid off. It's also when it comes to collaboration. Since SimScale is cloud-based, it's really tailored to the needs of, let's say, big project groups working at different locations. And especially from our customers from the AEC world, this is a very, let's say, valuable feature that because they are often working, let's say, in international remote teams around the world, and their SimScale's cloud-based approach make it very easy to share results and know-how inside the team. At the end of the day, there is one question which is raised every time, and it's related to security. And since SimScale is cloud-based, for sure some of your data are stored on our servers. However, we really put a big focus on security. So your data is actually encrypted twice, and without your permission and your password, even the SimScale team is not able to let's say, access your simulation projects and results. It seems like we have, again, some questions regarding the webinar recording. So just to make it clear, there's nothing you need to do in order to get the recording. We will send the link, I think, tomorrow or later at Thursday to all registrants via email. All right, and finally, let's also take a look at other industries where SimScale is used. So besides the AEC industry, which I already discussed with you, SimScale is also used a lot in the electronics industry for designing housings and cooling paths inside electronic products, as well as, let's say, in some more orthodox industries like the healthcare industry. We have customers which are optimizing implants using simulation. But actually simulation can be used everywhere where fluid flow is involved and where it's important to optimize the interaction between the machine or, let's say, your design and the surrounding air. And here you can see some other examples. For example, in the energy sector, CFD is used to optimize the shape of the plates of a wind turbine. And a similar application is the optimization of aerospace turbines. Or, for example, for consumer goods, SimScale is also used a lot to do virtual drop testing, for example, and so on. Well, and now let's talk about our today's topic. And as you know, we want to learn more about the application of CFD for HVAC system design and HVAC ducting design. And on this slide you can see a very typical example of a T-junk and a ducting design where we have calculated the flow field inside and visualized the flow field by using streamlines which are colorized by the pressure. And I mean, in general, there are hundreds of ways how to use CFD simulation in this industry, but I would like to discuss, let's say, the two most important scenarios. The first one is if you are a HVAC equipment manufacturer yourself. As you know, there are a lot of companies which are offering modular segments for HVAC ducting design, which can then be used by other companies to build their own custom ducting system based on that. And usually when it comes to design such segments, there are two things you need to do. First of all, you want to make sure that your design is working properly for different, let's say, scenarios and different circumstances. On the other hand, you also need to provide some documentation with your product. And when it comes, for example, to HVAC ducting segments or elements, you usually need to provide a loss factor for every segment. And in the past, or let's say the old way of determining this coefficients is really put the segment on a physical test rig and measure the pressure drop. And this is something where simulation can really help, because it actually allows us to virtually calculate the pressure loss and therefore to determine the pressure loss factors without having the need of manufacturing a physical prototype. And so CFD can be used by the designers and manufacturers of equipment to improve the design of the equipment and segments, and also to find out important parameters which they need alongside with the documentation of the product. On the other hand, CFD can also be used by contractors and companies which are planning HVAC systems inside buildings. And they usually, and this is something I want to show you in the next couple of minutes, they usually use simplified methodologies to calculate the total system performance of the HVAC system based on the characteristic of the different segments and elements they used. And one very, I think, famous, or let's say important procedure for this is the K loss factor method. And I know there are a lot of different systems. What they all have in common is that they are actually calculating the performance of the total system by treating the flow as a simplified Bernoulli flow, so a simplified pipe flow. And you have like different loss factors for the segments, and then you can calculate the overall loss factor based on the single factors. And this method is not very accurate in let's say in some situations, and the CFD can also help a lot if you want to really understand the real world behavior of your ducting system, and not only how it should behave, but how it will behave in reality, and also how it will interact with its environment, because all these questions are not considered inside the simplified analytical models. And therefore I want to directly show you a very simple example. So in the next 5 minutes we're going to take a look at this ducting system, and this model was created based on segments from a public available HVAC element library. So we built this geometry by adding at least, I would say, 1, 2, 3, 4, 5, 6, around 10 elements. And it's working like this, that we have a volume flow entering here with 0.5 meter per second, and we have 2 outlets which are open to ambient pressure. And first of all, let's take a look on how these problems are treated traditionally. So in this spreadsheet we have prepared a calculation of the pressure loss for that system based on the loss factors provided by the manufacturer. So as you can see, we have in the end we separated the model into different sections, to 4 different sections, and for every of the section we calculated the average velocity based on the cross section and the mass flow. We were provided with the loss coefficient, and based on that we were able to calculate the predicted loss. And some of this is the predicted loss for the whole system. And we actually did it for two models. We did it for a simple T-junction as well as for a T-junction with a contraction. And you can see both the blue dark bar is representing the pressure loss in Pascal, which was predicted using this analytical method, and the light blue one is representing the actual pressure drop, which was calculated using a CFD simulation. And what you can see is that for simple shapes, like just a simple T-junction, the results are very similar. So we're talking about a difference of, some percent, but whenever the geometry becomes more complex, there is a huge difference, and now it's nearly 50%. And the analytic methods are actually under-predicting massively the pressure drop. And this is actually the first very important learning. All these analytical methods used in the past, they are not necessarily bad, but they have the limitations. And whenever it comes, let's say, more complex changes of the shape of your HVAC system, or to explain it more generally, whenever it comes to big changes, let's say, in the physics of our flow field, these models are not anymore able to predict the pressure drop accurately. And a very good example for that is whenever we have a flow separation. Because whenever we have a flow separation, really the global, let's say, flow physics massively changes, and all of the single parts, when we calculate, or when the manufacturer calculated and measured the loss factors, it was all based on having a flow which is not separated. And this is just an example which shows when and why the analytic models can fail. And whenever they fail, CFD is the right tool to get the information you need. And now I will show you very quickly what is the process behind such a CFD simulation of a HVAC T-junction. So everything starts with importing the CAD model. And this is maybe the most important point. And here it's also very important to understand what is our CAD model. So in contrast to the manufacturing, where we actually need a model which is representing, let's say, the material of the ducting system itself, for our CFD simulation we need a CAD model which is representing the fluid domain. So we need a CAD model which is including the space inside our ducting system. And the first step, let me just quickly switch to the SimScale platform. So this is the SimScale platform. Everything is happening in my web browser, and this is the project I've prepared. Let's just quickly open the project. And yeah, then let me switch to full screen. And yeah, this is the CAD model. You can also see the other two designs. So we have this one where we have added a fillet here, and we have design 2 where we also added a radius on the other side. And yeah, it's quite easy. You can upload your geometry here, and you can choose different file format like exchange format like step, IGES, as well as interchange formats between or native formats like Autodesk Inventor, Parasolid, or Rhino. Then you have several operations you can apply, like scaling or splitting of your geometry. And then the first step of a flow simulation is to create the so-called mesh. And just to explain the background, as you can imagine, a computer can only storage a finite number of values, and therefore it's necessary to tell in advance your computer or the system how many values you want to calculate inside your model, and let's say how accurate you want to resolve your flow inside your model. And as you can see here, we used a very fine mesh, And so inside every of this, what we call cells, the solver will later calculate one value for temperature, pressure, and velocity. And you can actually create these meshes fully automatically, but you can also add manual refinements and stuff like that. And after you've created the mesh, the next thing or the next step is to set up your actual simulation. And in the first step, you choose which kind of analysis type you want to run. In our case, it's fluid dynamics incompressible. And for example, here you can also find some examples which you can directly import into your working space. Then you need to define which mesh you want to use, which material should be considered for the fluid inside your simulation. In our case, we just imported the material properties of air from our material library, and then you need to define the boundary conditions. In our case, we have a volumetric flow rate of 0.5 cubic meter per second. Entering here, we have outlets here and there, and all the other faces, remaining faces, are physical walls. Yeah, and then we actually can directly start our simulation. In this case, the simulation was performed using 16 computing cores, which represent 16 processors, and it took 300 minutes, so around 5 hours. Here you can see how the simulation converged. So this is let's say average error on our simulation, and it's quite small in the end. And yeah, once this is done, we can analyze the results. So we can, for example, take a look at the pressure difference, the pressure drop, for example. So this is a pressure at the inlet and the two outlets, and we can also take a look at the 3D result fields. This is our ducting system. We can now, for example, create a cutting plane, let's say, and so let's say in that direction. And then we can also move it. Now let's, for example, visualize the velocity distribution inside our. We can see we have this flow separations here and there, and yeah, you can create for sure screenshots, 2D plots, and do a lot of different stuff. Yeah, and as I mentioned, that's a process, and now I will show you how we use that simulation to improve the design of our HVAC ducting system. So, and again, this is what I told you about, the example between a good and a bad analytical prediction. And whenever we have strong intercomponent interaction between the different segments, our analytical prediction will not be very accurate, and there it's a very good point to start with CFD. Yes, this is what I already showed you. So as long as we have small changes and small interactions, we have a good agreement between the analytical results and the actual results, which can be simulated very precisely using CFD. And once we have some changes and complications like this contraction in the T-junction, the analytical models start to fail. And especially when it comes to more complex designs, it's very important, first of all, to understand and reduce the pressure drop, but also, for example, other aspects like flow homogeneity or vorticity can play an important role. And this is something where analytical models totally fail and where CFD will still provide us with a lot of information. So let's take a look at this animation. And this was created based on another simulation, and it really shows us exactly what is happening inside the duct, and where we have, let's say, some problems. For example, here you can see like we have this flow separation, and you can see like how after the separation our pressure massively drops. Yeah, now let's take a look at our design system and let's try to optimize it. So what we can see is that with the initial design we have flow separation at the sharp edges, and this creates large pressure drops, and these large pressure drops are contributing to our big pressure drop over the whole systems. And one approach we want to do or to test is just adding a radius to the, let's say, inner edge, and to see how this can reduce the effect. And if we add a radius, as you can see, we have actually a smaller pressure drop, but we still have a stagnation point which is present at the back wall here. And this stagnation point is still creating some kind of pressure loss, and therefore we will add another radius, or let's say reshape the T-joint to help the flow to run around the corner. And with this curved geometry on the black wall, the flow overall is guided better around the joint, and also the pressure drop is much smaller and it's more constant, unlike to the previous design. And you know, we took an initial design, did a simulation, took a look at the results, and then decided for the next design change. And now let's take a look, for example, at the pressure distribution with the 3 different designs. And here it really becomes visible what is happening. So the stagnation of this very first design, base design, really has an upstream effect on the flow. So you can see that we have a stagnation here and also a stagnation on the opposite wall, where we have in the near of the inlet, and that this results in this big pressure drop on the left and right side. Add in the cones or the radius helps a little bit, but however it leads to a new kind of flow separation on the one side of the junction with the radius, and we still have the effect of the stagnation of the flow at the back wall, which can also be seen at the high pressure area at the near of the inlet. And by adding this second radius, the stagnation at the back wall is removed, which also affects the flow upstream, so we don't have this high pressure area anymore. And especially take a look at the streamlines, really visualize that it's not only improving, let's say, the energy consumption of our system and reducing the pressure drop, but that it also has a very big impact, let's say, on the flow homogeneity and the air quality, especially if we have an HVAC systems where, let's say, the air is released into a room. With the base design, actually, just a small, let's say, area of the cross-section is used to deliver the fresh air, and you can see these blue areas where we just have like flow separation and recirculation, so the flow is not very homogeneous. Adding the radius improves it a little bit, but however still we have this flow separation, and the final design is even a smaller step back, because for some reason we have again a large separation on the right side. However, taking a look at the results, design number 2, or the final design, has a much lower pressure drop. So CFD not only explains us what is happening, but also why. Then, because the reason for this decrease in pressure drop can be found mainly in the fact that we don't have any stagnation point anymore, but on the other hand, the flow homogeneity is lower than with design number 1. And this was just prepared, in like a couple of hours, but it allowed us to reduce the pressure drop by approximately 45%. And based on that, if we would do some other design iterations, I'm quite sure we could even massively further decrease the pressure drop. And now let's try to summarize what we've done in the past. So for creating this simulation, it took 3 hours of my manual time for preparing the CAD model, uploading everything to SimScale, setting everything up. It needed another 12 hours to finalize all the computations. And just remember, we use 16 cores, so if you would do this on your local machine, it would approximately take you 16 to 20 times longer. And in total, we used 800 core hours for the simulation, which is a kind of unit which makes different simulations comparable in terms of the computational capacity which was used. In return, we were able to improve the efficiency, we ensured the accuracy of our prediction and saved a lot of time. And finally, we were able to massively reduce the pressure drop and improve the flow homogeneity. All right, and that will be everything from my side. And now it's time for your question and answer. So whenever you have a question, just feel free to write it into the question toolbox, and I will try to answer it as good as I can. So the first question is by Nirav, and Nirav wants to know how credible calculated pressure drop by CFD is compared to the actual experimental data. Nirav, that's a very good point, and in general, a simulation is only as accurate as, let's say, the assumptions are which were used to prepare the simulation. When it comes to ducting design, a big advantage is that those flows usually have a very, let's say, low Reynolds numbers to compare to other phenomena like external aerodynamics of an airplane, for example, and therefore usually the reliability of CFD results is very, very high. So in this special case, we did not do any physical testing, but our solvers were validated in general for a lot of different applications, including internal flow. And our website on simscale.com, you will find a kind of library with a lot of different validation projects where we actually validated our simulation results against physical experiments and analytical results. The next question is by Walid. Walid wants to know how do we give the input of duct surface roughness of different materials as we use more than 2 different duct materials. That's a very good question, Walid, and this is something which you can easily specify yourself directly in SimScale. Let me just give you an example. So for example, you can create a new boundary condition, go on custom, and then we have different boundary conditions, and there's also a boundary condition which can include wall roughness described by some analytical parameters. Harald wants to know if it's possible to simulate the temperature loss caused by this high turbulent flows. Yes, for sure this is possible. For this analysis type, just to make it simpler, I did what we called cold simulation, so I didn't consider a change in temperature. However, it's possible without any problems. Therefore, we have a little bit different analysis type, which also considers temperature and convection effects. Then there's another question by Nirav, and he wants to know if CFD is really cost-effective to a design consultant. And he said that they're usually carrying on considering 10 to 30% safety factor, and if I could give him some more examples where he can use CFD in other aspects of HVAC design. Dear Nirav, for sure it's a pleasure to discuss with you that aspect of CFD. So first of all, regarding your first point with the safety factor, I would say that in general, for a lot of, let's say, very simple systems, you may be right, and using a safety factor will help. However, just this small example showed that analytic tools really start to fail if we have, let's say, more complex geometries or more interaction between several parts. And just in this case, the difference was 50% for a very short system. And if we have, let's say, larger complex systems, so a lot of times the safety factor is not accurate enough. Besides this, I think CFD is also very helpful, and not only if it comes to prediction of pressure loss, but especially when it's, for example, about to understand the interaction between, let's say, your HVAC system and the environment. Let's give me an example. Let's say you're going to design the ventilation system which should be based on ducting for a large office space. Then it's not about to deliver the right amount of air into the rooms, but also to make sure that the air leaves, for example, the grills of your HVAC system in a way that the thermal conditions for the occupants are good. And especially their analytical tools will not provide you with any information. And we have, for example, a customer which is designing HVAC systems for schools. And there it's very important to make sure that for, let's say, every scenario, there's the right combination of airflow temperature and airflow speed in order to reach thermal comfort, and their CFD is very helpful. So not only when it comes to what is happening inside your ducting system, but especially when it comes to how the flow leaving your ducting system is interacting with the environment. Well, let's see, we have some more questions. Amma wants to know if we are able to run steady state and transient simulation. Yes, for sure, Emma. You can run both kind of simulations with SimScale, and you also can do LES as well as use turbulence models depending on what kind of simulation you need. Yeah, let's see, we have more questions. Give me just 1 second to bring them into the right order. Simone wants to know about the convergence analysis and turbulence model we use to simulate this case. So for that case, we use the K-omega SST turbulence model, which is besides the K-epsilon model, let's say the most common model for simulating internal flows. And the great thing about the K-omega model is that it's quite robust. And regarding the convergence of our simulation, since we have some experience with simulation, we usually don't need to do a convergence analysis, and based on our experience we actually know how to create the mesh. But in this case you can see that all the, let's say, flow variables like pressure, velocity components, turbulence quantities were converged after 5,000 iterations. And also, which is much more meaningful, is the fact that our pressure values at the patches always also converged. So based on this, you can be quite sure that this results are converged. Then there is a question by Justin, and he wants to know if the ASHRAE fittings database values have been simulated, and if yes, how to do the simulated results, how to compare them to the published data. That's a very good point, and actually this ASHRAE fitting database use this, let's say, semi-analytical approach of using, in the end of the day, loss factors for different kind of data sets. So CFD here is more something that you would use in addition to ASHRAE fitting database whenever you think that your design is so complex that the fitting database might not be precise enough, or whenever you want not only to understand, and this is quite familiar to what I was discussing regarding the question of accuracy, whenever you are not sure if your system is maybe too complex to be simulated or to be analyzed using this database values. Then some people asked why we only had such a small pressure drop inside our system. Especially this question was raised up by Walid. Well, I know in reality such systems are much bigger and much longer. In this case, to keep things simple and to make it you able to directly understand what we are doing using the simulations, we used a small system. And for sure in such a small system, which is just a small part of the system, the pressure drop is small. However, if you would think of a real-world system considering of a lot of these small systems, you would end in a higher, not neglectable pressure drop. Then Paul wants to know if it's possible to perform transient and steady-state simulation of rooms with heat sources to see the evolution of temperature with time. Yes, Paul, for sure this is possible, and we also have some information regarding that on our website. We have some older webinars and workshops dealing with that. And as I mentioned, you can do transient simulations. However, a lot of our customers also answer this question using steady-state simulation. If you're interested in that special application, just reach out to me by email or take a look at our website. Then Walid wants to know how complex duct access-force geometries should be modeled. For example, the flow through each volume control damper and sound attenuators. And his basic question is using this simulation if he can determine the opening angles of blade and each volume control damper, if they are modeled good enough with the 3D geometries. Valid, for sure, this is possible, and here the only thing limiting yourself is in the end of the day having the right CAD model. And in this special case, what you would do is to simulate, let's say, the dampers as static parts, and then you would like measure the momentum, for example, or the force acting among them, which can be then translated, or these values can be translated and used, let's say, to get to determine the opening angles of the blades. Scott wants to know how does the scale of the system influence accuracy of the simulation, and that's a very good question. Actually, that's a great thing about fluid flow simulation. You still have this Reynolds number phenomena, so it allows us to compare, let's say, different cases which are identically from a geometrical point of view but have a different scale. But in general, I would say the scale does not make a big difference. So it's just in the end a question of units. All right, it seems like all the questions were answered. Thank you very much for your time. It was a big pleasure. In the case you got another question, feel free to reach out to me using email. Thank you very much for joining, and I wish you a wonderful rest of the week and see you soon. Bye.